So, hello? There we go. All right, so last time I just barely gave a teaser for some kind of heuristic that would let us predict how many number fields there are asymptotically with some particular Galois group and some local conditions at finitely many primes. So I'm now going to talk about this heuristic for counting number fields. And as I mentioned before, this heuristic has roots in work of Mala and then was further refined by Bhargava. But the way that I'm going to state it is so strong that it has lots of counterexamples. And so I hesitate to attribute it to them as a conjecture and then tell you that it's wrong. They, of course, understand that, and it really should, unlike the Cohen-Lindster heuristics, which should be interpreted actually, I think, as conjectures. I mean, people call them the Cohen-Lindster heuristics, but they mean Cohen-Lindster conjectures. These are actually heuristics, and as far as I'm concerned, it's an open problem. I mean, it's an open problem to decide when the heuristics make sense and when they don't. So these are, so these are much not to be interpreted as what we think is true, but a guideline of something that might possibly be true, and maybe we can understand in what cases it's true, and when it's not true, why something else is true. All right, so we're going to fix a permutation group. I'll call it gamma. And for each place P of Q, we'll have some local conditions. So we have some sigma P set of homomorphisms, say from GQP to gamma. So we're interested, so by counting number fields, we want to count maps from GQ to gamma. All right, so we already talked about, well, I guess if it was really counting number fields, gamma should be a transitive permutation group, but I suppose we can do the same for non-transitive, but it probably makes sense to imagine that gamma is some transitive permutation group. You might even be imagining gamma is Sn. That's a particularly nice case. And so to count gamma number fields, we've said that's the same as counting these Galois permutation representations. And so then these sigma p's are supposed to say, well, we don't want to count all of them. We want to count them with restriction. If we restrict them to the decomposition group, GQP, that should actually be one of our favorite elements of sigma p. So for example, if we wanted to count things that were, say, split completely at 7, for every place that wasn't 7, we'd just allow all homomorphisms here. We'd let sigma p be all homomorphisms because we don't want to put any restriction at places other than 7. And if we wanted split completely at 7, then sigma 7 would only have a single homomorphism. It would be the trivial map there. And so if we let sigma p be everything when p isn't 7 and just the trivial map when p equals 7, that gives us an example where these local conditions just say split completely at 7. Okay, so we're counting gamma number fields with some local conditions. The heuristic is that we'll build a Dirichlet series. So I'll call it D gamma sigma. So it depends on gamma and sigma. So all these, we'll call sigma as the name for all the local conditions together. So that's going to be a Dirichlet series. And we've got this C gamma, so this is a constant which depends on gamma. So not going to talk about that quite yet. And so here I'm going to have a product over all places. So I'm using this sort of abusive notation. I mean to also include the infinite place, but I mostly want you to be thinking about finite places, so I'm calling them P. So product over the places, and now when we were counting abelian number fields, we could build something, a Dirichlet series like this, that actually, by class field theory, literally counted the abelian number fields, because we had that the maps to gamma abelian could exactly be given by products of maps from ZP star to gamma for each P. And so what I'm going to do here is now write something which gives the same idea, but when gamma is not abelian, it will not be counting anything. It will just be the same kind of thing, the same kind of idea that we imagine we can put local things together and they sort of glue together to global things at the same rate. Okay, so what I'm going to put here is, so 1 over the size of gamma times a sum over the maps rho sub P in sigma P. So I'm summing over my allowed local homomorphisms, and then I'll take the discriminant of rho sub P to the minus S. Okay, so let's just check. So let's just check that this agrees. So if gamma, say, was abelian, and sigma allows everything, okay, then what does this local factor look like? So it's 1 over the size of gamma. And now I'm looking for maps from QP star to gamma, say rho, discriminant rho to the minus S. Well, if I've got a map from QP star to gamma, I can think of it as two things. There's the map from ZP star. So the multiplicative group QP star, right? There's the ZP star, and then there's the P. So the P can go. The P generates, a free abelian group here. It could go to any element of gamma, and it doesn't affect the discriminant. So when I cancel the fact that this P could go to anywhere in gamma with this 1 over gamma factor, I find that this is exactly the local factor that in the abelian case actually literally does make this a Dirichlet series counting extensions. All right, so for general gamma, the principle or heuristic, the heuristic, maybe I'll call it heuristic / principle, is that the asymptotics of the coefficients of this Dirichlet series that we built should agree with the asymptotics of the actual count. This was just our notation for the count. This is gamma number fields satisfying the sigma conditions. Okay? So even though we, at least as far as any theory we have, for non-abelian gamma, we can't actually piece together local gamma extensions to build global gamma extensions, we maybe think that on average, if we just wonder how many there are, maybe that's a reasonable heuristic for predicting how many there should be. So this local factor here at each place P in this Euler product for this Dirichlet series, it might look kind of scary, but we remember that in the abelian case, they were pretty simple. Like when gamma was z mod 2, this factor here, it was just 1 plus p to the minus s. And when gamma was z mod 3, then this local factor was just 1 when p was 2 mod 3, and it was 1 plus 2 p to the minus s when p was 1 mod 3. And so actually, these local factors, even in the non-abelian case, are pretty straightforward to understand as long as we restrict to tame places. So tame places, and let's say tame finite places, so P not dividing the order of the group G. Okay. So then, this local factor, I'm summing over. For now, let's just imagine that gamma is everything, that I haven't put any in local restriction. So I'm summing over homomorphisms from GQP to gamma, and then I just need to put them in with their, oh, sorry, this is discriminant of rho. Yeah, minus s, okay? So because we've taken a P that doesn't divide the size of gamma, any ramification here has to be tame. So in particular, the image of the wild inertia group has to be trivial here. There's no wild inertia. And so this factors through the tame quotient. So rho must factor through the tame quotient of GQP. So it turns out that this is actually very easily described, and this tame quotient is as a profinite group generated by just two elements, by x and y, with relation x, y, x inverse is y to the p. Okay? So if you only care about tame extensions, this is a complete description of like the absolute tame Galois group of a local field. So very, very different than what we know for global fields. In fact, such a description in terms of generators and relations is known for the whole absolute Galois group of QP, even including the wild part. It's much more complicated and unfortunately less useful description, but it is literally a description in terms of generators and relations of the entire absolute Galois group of local fields. So we know a lot more about local fields than we do about Q, and this is one example. So this this y, so I'll just make some remarks about this. So here, y generates the inertia subgroup in this tame quotient. So that's may perhaps align with the fact that you know that tame inertia has to be cyclic. So if you have a tame inertia subgroup, it has to be cyclic. Well, there's the one generator, and X is the lift of Frobenius. So those are familiar players. So now this local factor, well, here, maybe I left all the space. I'll just write it here. Okay. So after we know this, what this GQP looks like, at least in its tame quotient, we see that this is just the number of x, y, choices for x and y in gamma such that x, y inverse equals y to the p, and then we need the discriminant. So I will now, that discriminant depends only on the ramification, so only on the image of inertia, so only on y. So I'll call it the discriminant of y now. Minus s. Okay. So now, what looked like what looked like something involving all these Galois representations. Now this sum is entirely defined in terms of group theory, in terms of elements of this group. It's now a sum that, at least for this part of a sum, you could give to a group theorist. I'm just looking for pairs of elements in a group gamma that satisfy this relation. Okay, so there's the discriminant, and it turns out that, so using that the discriminant is the Artin conductor of the permutation representation. So one understanding of the discriminant as an Artin conductor, it turns out that the discriminant of y equals p. Well, it had to be p to something because this was a extension of QP, so it was only going to be ramified to p. That was the only prime. So to some exponent. So it's n. So what was our n? I'll remind you that gamma was a subgroup of Sn. So we were talking about a degree n number field. So it's n minus the number of orbits of y. So y is an element of gamma that was a permutation group. So gamma is a permutation group that acts on n things. All right, so it has, on those n things, there's some number of orbits. And if we take n minus the number of orbits, so a very simple thing just in terms of what this permutation group is, gives us the discriminant here. So that's actually also completely concrete. I'm just going to take it a little bit further. So so if I think of it from the point of view of a y, okay, I've got, say I first sum over y. Now I want to know, well, how many x's work? Okay? So how many x's can I choose? X such that x, y, x inverse equals y to the p. Discriminant. Well, I could have put that discriminant over here, but I didn't leave that much space. Okay? So, so how many x's work? Well, first of all, is y conjugate to y to the p? If y is not conjugate to y to the p, then there are no choices for x. So I only need to even be summing over y that are conjugate to y to the p. All right? So, and if y is conjugate to y to the p, how many x's get it there? By the orbit stabilizer theorem, I've got the whole group gamma acting on y, and the size of the orbit is the size of the conjugacy class of y. So the number of x's that take any particular, take y to some particular element in its conjugacy class is just the total number over the size of the orbit. So just writing that down. So first of all, I only want to be summing over y that are conjugate to y to the p. I'll use this little tilde to mean conjugate to. And then the number of x's I have here by the orbit stabilizer theorem is the size of gamma divided by the size of the conjugacy class of y. Discriminant y to the minus s. So this sum, it's even, so first of all, these gammas are going to cancel, and then if I'm summing 1 over the size of the conjugacy class, say, over all the elements of the conjugacy class, that just gives me 1 for each conjugacy class. So the local factor is, so here, now I'm going to sum over conjugacy classes of gamma such that they're equal to their pth power. Discriminant of y to the minus s. So it's, so now I guess it's pretty, remember our first example would be like gamma equals z mod 2z. Now we can very simply see, well, what are the conjugacy classes? Where this happens, okay, this is just local factor is 1 plus a p to the minus s. But if, for example, we had our gamma was z mod 3z, the other abelian example that we already did, so conjugacy classes doesn't mean anything in the abelian group, but whether y could possibly be y to the p, I've written this multiplicatively here, but this is the group operation in here, depends on whether p is 1 mod 3 or not. So when p is 1 mod 3, all 3 elements have, pz equals p, but when p is 2 mod 3, what? Oh, sorry, equals z, thank you. Only z equals 0 has pz equals c. So that explains the difference in the factors that we saw there. Now, maybe I'll use this space. There are always, of course, some primes p that are congruent to 1 mod the size of gamma, right? So, or some primes in that arithmetic progression, and at such p, you get particularly simple. You just get a sum over conjugacy classes of discriminant of y to the minus s, because of course y to the p is 1 if p is 1 mod gamma. Okay. So I hope I've convinced you that that this heuristic is pretty accessible. You build a Dirichlet series out of these local factors. The local factors are incredibly concrete in terms of the permutation group. They've got the, it's just about the conjugacy classes. You've got this counting orbits and the discriminant. So these local factors are incredibly concrete. There's a couple of them that are bad. We didn't talk about the tame, we only talked about the tame. We didn't talk about the wild factors, but there's only a few of those, and so they won't affect the asymptotics, at least, of the rightmost pole of the Dirichlet series and the counting. So we can understand a lot about what this predicts for the order of growth, if not the precise constant, even without ever touching a wild factor. In particular, this heuristic predicts what I guess we can call Mahler's conjecture. So actually, it's not completely trivial to see that the heuristic predicts this. I mean, in particular, even for these Dirichlet theories, one still has to find the pole and a little bit of analytic continuation to see that this heuristic predicts this. But it indeed does that. Well, I won't actually. Okay, so this is a constant depending on gamma. And this is okay, so A and B are some numbers depending on gamma, and this is a constant. Oh, sorry, not equals, but is asymptotic too. So Mahler for every group conjectured completely in terms of just the group theory numbers A and B. He didn't conjecture this K, but numbers A and B, such that he thought these asymptotics were true. And I'm not going to say now what the A and B are. It doesn't matter so much, and it essentially comes out of just the sort of combinatorics here of these, or group theory of these permutation groups. So for every group, it says, for every group, you just can very concretely see through what A and B are, and it says that the gamma number fields up to discriminant x grow asymptotically like this power of x times this power log of x. All right. So it predicts 1, and it predicts 2. It predicts independence of local behaviors at different places. Okay. All right. So among the many things that this heuristic predicts, it predicts both of these things which have counterexamples. So both of these have counterexamples. So Kluners gave a specific group gamma where you can see that the count is actually bigger than Mahler's prediction. So so maybe I'll say for 1, gamma C3 wreath C2, and gamma is bigger. Okay? And so that it doesn't even have to do with the constant, which, I mean, this actually sort of, in some sense, it predicts a constant. This just has to do with the order of growth, and it's wrong, for example, for this group, though Turkelly has a paper that I think explains from this perspective that Jordan has been talking about, the sort of geometric analytic number theory predictions from the function field side, why we should have guessed that, and maybe how we could sort of fix the order of growth in the conjecture. But then we've already seen, of course, for abelian, I already said, we didn't really go into all the details, but I already said that for abelian gamma that are not elementary abelian, so not z mod pz to the k, independence fails. And so, all right, so that's the bad news, is that this kind of heuristic or principle, it's not a conjecture that anybody makes and believes in all cases. But the good news, or the surprising thing is, yet in many cases, it is right on, just exactly right. But yet, given, especially in light of these counterexamples, perhaps like it is, but yet it is right sometimes. And I would love to understand when it's right and when it's wrong and why, but I don't. Okay, so let me just say that for gamma equals S3, so by Davenport-Heilbronn, which I'm going to, in fact, talk about, this heuristic gives correct answers. Heuristic gives correct answers. And so that's S3 in its three-dimensional permutation, or permutation representation on three things. There's also the gamma equals S3 and S6. So that's a result of Bargava and myself that gives the correct answer for gamma equals S4 and S5 and just the expected permutation representations. These are results of Bargava, that these answers are as predicted by the heuristic. For gamma equals D4, Cohen, Diaz, and Olivier show that the order of growth is right, but in another paper of Cohen, I think essentially shows that but otherwise the conjecture is wrong. So we've got a sort of half right here. Otherwise the conjecture is wrong. One doesn't have the independence or the relative proportions of local behaviors that the conjecture would predict. So let me see. I think that's about the boundary of our knowledge about this. So it's a heuristic. Sometimes it's right, sometimes it's wrong. What does it mean? I don't know. So very tantalizing. I think there's a lot to understand about counting number fields. And that whole story, I mean, I did that whole in terms of discriminant. And maybe after I talked about abelian number fields, you should be thinking, why did she do it by discriminant? Really, I shouldn't have done it by discriminant. I should have done it by some yet to be specified counting invariant, that is the perfect counting invariant that we haven't found yet. But I guess I just did it with discriminant out of tradition. That's what people first thought of counting number fields by. So now I want to talk a little bit about Davenport-Heilbronn. Okay, so how does one count? So counting cubic non-Galois number, or not necessarily Galois, number fields. So how does one get your hands on cubic number fields? For abelian Galois number fields, we have class field theory. That was something that told us something about number fields with abelian Galois group. The Galois closure here will, when these cubic number fields are not Galois, will be S3. So can't use class field theory. There's no nothing standing in there to tell us what the Galois, absolute Galois group can map to S3, what those maps are, what those permutation representations are. We just don't have some kind of general theory. But what there is in this case, which is particularly special, is a parametrization of cubic rings. So I need to get to cubic rings. So by a cubic ring, I just mean a ring which is isomorphic to Z cubed as as an additive group. So for example, if K is a cubic number field, OK, the maximal order in K is a cubic ring. There are other cubic rings. Here's another cubic ring. All right, that's another cubic ring. That is not a maximal order in any number field, but anyway, so there are cubic rings. Some decent, some good proportion of them turn out to actually be maximal orders in cubic rings, and so the strategy is going to be to count cubic rings and then sieve for ones that are actually maximal orders in fields. So I've done a lot of sieving. So I'm mostly going to focus on counting cubic rings and why it is we can do that. So if I have a cubic ring R, I can always take a basis, a Z basis, as a Z module. So I'm going to call it 1 big W and big T. And WT is the product of those two elements. Well, I know what 1 times W are and 1 times T. That's why I called it 1. But WT is something. It's, say, Q plus R, W plus ST. For some Q, R, and S that are integers. So by taking omega equals W minus S and theta equals T minus R, I can get a new Z basis for R, 1 omega theta. So I just shifted. This was like a lower triangular transformation of my basis. I just shifted W by a multiple of 1 and T by a multiple of 1. And in this basis, now, if you just check when you multiply out, you don't get any omegas or thetas in this multiplication. You just get a multiple of 1. Okay, so of course, that's not all I need to know about my cubic ring. How these two things multiply, I also need to know what omega squared is and what theta squared is. So okay, so there's something, they're this for some M, B, A, L, D. So for some integers, they have to be in the ring, so I have to write them in this way. I put these signs here just so that later things will be nice. So if you were doing this the first time, you would not put these signs here. You would just say, okay, I've got some integers everywhere. So every cubic ring has to have such a multiplication table. And actually, there's something that I know about this multiplication that I haven't yet used. The multiplication is associative. So that means if I take omega squared and then I multiply it by theta, I can use these rules to see what it is. And then I could see what happens if I took omega theta and then multiplied it by omega and see, I should get the same thing. So I haven't used that fact yet, and it turns out that associativity, when you write out the associativity relations, they're exactly equivalent to the following equations in these parameters here, that n is minus AD, m is AC, and L is minus BD. So that means that if I have a cubic ring, I've got these 4 numbers A, B, C, D, and they determine N, M, and L. They're A, B, C, D, they're running the whole show. In fact, one can check that given any A, B, C, D, taking N, M, and L to be these products, this actually defines a cubic ring. So associativity, commutativity, everything you need works out, and this actually defines a cubic ring for any choice of A, B, C, and D. When we chose our basis like this so that omega theta was just a multiple of 1, we'll call this a normalized basis. And so from what I've said, it follows that cubic rings with a choice of normalized basis exactly correspond to quadruples A, B, C, D of integers. So every cubic ring with a choice of basis gives me an A, B, C, D. Every A, B, C, D gives me such a cubic ring. So this is what the kind of thing I mean by a parameterization of cubic rings. But of course, I was interested not in maximal orders and cubic number fields with a choice of basis, but just maximal orders. So I want to get rid of this choice of basis. So the choice of basis, after I've normalized, there's basically a GL2 that I can do to change basis. So there's a GL2Z here that changes basis. And so it follows that there's some GL2Z over here, because if I have a ABCD, it's a cubic ring with a choice of basis. I change that basis. The reason it's a GL2, I mean, first of all, you have to fix 1. So it couldn't be all of GL3. And this normalization really is like taking a basis of R mod Z. So there's 2 dimensions left to sort of change around. So if I had an ABCD, I'd make a cubic ring. I apply GL2, I've got another ABCD. So there is some action of GL2, ABCD, such that cubic rings up to isomorphism exactly correspond to GL2Z classes of A, B, C, D. And the question is, you probably want to know what this is. So we're going to count cubic rings by counting GL2Z classes of these quadruples. And it would help if we actually had some kind of reasonable description of how GL2Z acted on these quadruples. And it turns out that it's quite nice. If we write f of xy to be ax cubed plus bx squared y plus cxy squared plus dy cubed, and g is in GL2z. So now I've turned my A, B, C, D, I've made them the coefficients of a binary cubic form. So I'm going to just package them into this one form. Then I can tell you how G acts on the form, and it acts almost by just applying GL2 to x and y. So it's almost that, and there's a twist by the determinant. Okay? So that doesn't see, of course, much action over z. It's just plus or minus 1. All right, so ignoring that, basically the GL2Z action here is the GL2Z action on binary cubic forms. So to count cubic rings, we need to count GL2Z classes of binary cubic forms. All right, and that is the parameterization that lets you actually make some progress, and is how Davenport and Heilbronn essentially originally, I mean, certainly they were counting GL2Z classes of binary cubic forms. That's how they proved their theorem. counting these classes. So I want to say a little bit more about, why binary cubic forms? Everything I said was like literally mathematics. Okay, I said, you check the associativity relations, like you get these things. Oh, you check what the change of basis gives you. It gives you this, but why? Why is that what we saw here? Why was it, why do cubic rings have something to do with binary cubic forms? So I want to tell another story. So a binary cubic form, such an F here, so I'm thinking about these binary cubic forms, where does that live? What kind of object is it? So because it's a homogeneous form here in two variables, I should think of it as being on a P1, right? And these are integers, so it's a P1 over the integers. So I'm going to draw a picture of P1 over the integers. So first I want to draw a picture. Here's my picture of the integers. All right. And so it's one-dimensional. That was the important fact in that picture. And here's my picture of P1 over the integers. So that's a two-dimensional thing. So over your favorite point or prime of the integers, this just looks like a P1 over FP, so a more familiar kind of thing, a more familiar one-dimensional thing, but it's one-dimensional there over every prime, and putting it all together, it's a two-dimensional thing. So this form, f of xy, because it's homogeneous, it's the kind of thing that you ask for its zeros in P1, right? You say, where does it vanish in P1? So it cuts out, if we look at the vanishing locus of f of xy, it cuts out some I'll call it, say, VF for where f vanishes in P1 of z. And I'll draw a picture of what that might look like. It might kind of look like this. Right? That's what it could look like. So what are these lines? So if P divides A, B, C, and D, then when I reduce this form mod P, it's just the zero form. And so where does zero vanish? It vanishes everywhere. So if P divided A, B, C, and D, I would get a whole line here, a whole P1. So if that was really over P, that would be a whole P1 over FP over that P. And if like P to the 7th divided each of these, I'd not just get a P1, but I'd get this really thick non-reduced P1, all right? So I get a vertical fiber. Okay. There's actually one example of F that doesn't look like this at all. That is when F is identically 0. A, B, C, and D are all 0. That actually still corresponds to a cubic ring. Then you get all of P1. In that case, it's not maybe the best way to interpret things. There's a really nice story there, but I won't go down that rabbit hole. So if say P, let's say if the coefficients are relatively prime, so there's no P that divides all of them, then the picture, I won't get any of those vertical fibers. Then the picture will look like this, that at least geometrically I get 3 points in every fiber. So geometrically over any algebraically closed field, this has 3 roots up to multiplicity, with double roots or whatever. So here's like some multiplicity. There's somewhere you got a double root. There's somewhere you got a double root. But basically, there are 3 points in every fiber. So it looks like a triple cover of spec Z. And of course, that's exactly what when OK is a ring of integers in a cubic number field K, spec OK it's just a cubic cover of spec Z, a degree 3 cover there. All right, so in fact, when F is not 0, one takes the global functions, global functions, so H0 sort of VF, so the global functions, even when they're vertical fibers, are always a cubic ring, and they are the cubic ring associated to F. So that's actually sort of a theorem, and it gives the same cubic ring as above. And when we don't have any fibers here, this scheme is actually affine, and so its global functions are just okay, and it's spec of its global functions, and we see the cubic ring there. So now I want to point out that nothing that I said in this geometric story relied on 3 in any particular way. All right? There just would have been more curves of this curve here if I had had a binary inic form. And in fact, this construction, gives a map from binary inic forms to rank in rings. But I will leave us with that cliffhanger. Yet, unfortunately, we haven't counted rank in number fields for every n. So when we're back, I will finish the story and tell you what's special about 3. All right, thank you.